The ice is 1.8 meters thick here. The CCGS Louis S. St-Laurent hits it at 3 knots. Not fast, deliberately not fast. At 3 knots, the ship's bow rides up onto the ice surface, and the vessel's weight, 11,596 tons fully loaded, does the work. The hull presses down. The ice does not yield immediately. For a fraction of a second, the entire mass of the ship is balanced on its bow over a sheet of first-year Arctic ice, and the ice is deciding whether to flex or fracture. It fractures. The sound is not what most people expect, not a crack. More of a deep, sustained compression, a groan that moves through the hull and into the deck plating under your feet, felt as much as heard. Then the bow drops as the ice sheet breaks into slabs, and the hull shoulders them aside. And the ship moves forward another 3 meters before the next section of ice stops her again. 3:19 a.m. The sun has not set. It is July. This is the Arctic. The ice officer on the bridge is watching the ice ahead through 7x50 binoculars, reading the surface the way an experienced driver reads a road in rain. The color tells him things. White ice is air-rich, younger, more brittle. It fractures more easily. Blue-green ice is older, denser, has less trapped air. It flexes rather than fracturing, and flexing ice is harder on the hull. The dark patches to the northeast are open water leads, navigable lanes where the ice has already moved or melted. He plots a course that uses the leads where possible and powers through the consolidated ice where necessary. The officer of the watch on the St-Laurent has 13 Arctic seasons behind him. He is not guessing at the ice. He is reading it. And the ship, 120 meters of specialized hull, diesel-electric propulsion, 27,200 horsepower across 3 shafts, is responding to his readings with the precision of a tool that was built for exactly this purpose. The Canadian Coast Guard operates the largest civilian icebreaker fleet in the world. 18 vessels of varying capability, from the heavy icebreakers that operate in the high Arctic to the medium and light icebreakers that manage winter navigation on the St. Lawrence River and Gulf, the Great Lakes, and the Atlantic approaches. The fleet's operational mandate is broad. Arctic sovereignty operations, resupply of remote northern communities, aids to navigation maintenance, search and rescue in ice-affected waters, scientific support, and the management of winter commercial navigation on the St. Lawrence Seaway system. Each task requires a different capability. Each capability requires a different ship. The heavy icebreakers, as the St-Laurent, the Terry Fox, the Henry Larson, are purpose-built for multi-year Arctic ice, capable of sustained operations in conditions that would trap any other vessel. Their hulls are shaped differently from a conventional ship. Their machinery is sized differently. Their systems are designed for a failure mode that most maritime engineers never have to consider, being frozen into the ice for days or weeks or longer. The medium icebreakers work the margins, the areas where ice forms seasonally, where navigation is possible but dangerous without assistance, and where the commercial shipping that keeps Atlantic Canada and the St. Lawrence system moving depends on an icebreaker having already been through. The light icebreakers do the close work. Harbor approaches, river channels, the kind of ice management that keeps ports open when the temperature drops. Together, they are an infrastructure system. Water infrastructure, just frozen. The hull of an icebreaker is not simply a stronger version of a conventional ship's hull. It is a different shape entirely. A conventional ship's hull is designed for hydrodynamic efficiency, a fine bow entry, relatively vertical sides, a form that moves through water with minimum resistance. This hull in ice is catastrophic. Ice hits the bow directly, and the force is transmitted into the hull structure. Enough ice at sufficient thickness, it stops a conventional ship and can crush its sides. An icebreaker hull is designed to ride over ice. The bow is sloped, typically at 20 to 30 degrees from the waterline, so that instead of hitting the ice edge on, the hull slides up onto the ice surface. The ship's weight then fractures the ice from above. The broken slabs are directed outward and downward along the hull's curved sides, cleared from under the keel by the sloping underwater hull form. This riding and braking motion is called ramming in heavy ice conditions. It is not aggressive seamanship. It is the designed operational mode. The hull steel on an icebreaker is significantly thicker than on a conventional vessel, particularly in the ice belt, the section of hull that contacts ice at the waterline. On the Saint-Laurent, the ice belt plating is 31 to 40 millimeters of high-strength steel compared to 12 to 16 millimeters on a comparable conventional vessel. The frames behind the plating are heavier and more closely spaced. The transverse bulkheads are reinforced. The structure is designed to take a sustained beating, because that is what it receives. The diesel-electric propulsion system on a heavy icebreaker is a deliberate engineering choice. A conventional diesel mechanical system, engines connected directly to a gearbox and shaft, is efficient and well understood, but it lacks the ability to respond instantly to load changes. In ice, load changes are constant and violent. A shaft hitting a large ice fragment can spike from full load to zero to overload in less than a second. A mechanical system absorbs these spikes poorly. Gearboxes fail, and these shafts crack. A diesel-electric system interposes a generator and an electric motor between the engines and the propeller. The engines drive generators. The generators produce electricity. The electric motors drive the shafts. The motors can absorb torque spikes that would destroy a mechanical gearbox. Electric motors tolerate stall loads that no mechanical transmission can handle. On the Saint-Laurent, 6 diesel engines drive 3 electric propulsion motors. Total installed power, 27,200 shaft horsepower. The 3 propellers, 1 forward, 2 aft on the Saint-Laurent, can be operated independently at varying speeds and in varying directions, giving the ship a maneuverability that a single shaft vessel cannot match. In tight ice, this matters enormously. A ship that can walk sideways or rotate in a radius shorter than its own length, it can extract itself from situations that would trap a conventional vessel for days. The forward propeller, a feature not present on all icebreakers, is used for a specific technique called stern-first ice-breaking. The ship backs into thick ice using the aft propellers to drive and the bows slope to help ride up, while the forward propeller draws cold water from ahead under the hull to lubricate the ice contact surface. Cold water lubricates ice contact better than warm water. The forward propeller is, in part, a friction reduction system. 7:45 a.m. The Saint-Laurent has reached a section of multi-year ice, the kind that has survived at least one summer melt season and refrozen. Multi-year ice is identifiable by its rounded pressure ridges and its blue-white color. It is denser than first-year ice with less trapped air, more like freshwater ice in its mechanical properties. The ice officer calls for a speed reduction. At 1.5 knots, the bow rides up and the ice resists. The vessel's weight builds on the ice sheet. The hull groans. The ship stops, backing off. The officer backs the ship 50 meters astern, then drives forward again, using momentum to supplement the ship's weight on the ice. At the moment of impact, a controlled impact, precisely timed, the ice fractures along a pressure ridge that the officer identified through binoculars before the run began. The channel opens. This is called backing and ramming. It is the technique for the heaviest ice conditions. It is slow. Progress can be measured in hundreds of meters per hour rather than nautical miles. And it places the highest structural loads on the hull that the ship will ever experience. The officers who direct this technique are trained for years before they are trusted with it independently. Not because the procedure is complicated, because the judgment required, reading the ice, timing the run, choosing the attack angle, deciding when to back off rather than push further, is not proceduralized. It is developed over Arctic seasons in situations that classrooms cannot simulate. The engineering spaces of an icebreaker are a study in redundancy. The Saint-Laurent carries enough fuel, 2,800 tons of marine diesel, for approximately 40 days of operations without resupply. The fresh water capacity supports the crew for extended periods. The provisions stowage is designed for multi-month deployments. There are backup systems for backup systems, 2 independent steering systems, either emergency generator capacity sufficient to maintain critical navigation and life safety systems, if all main engines fail, hull heating systems to prevent freezing of internal piping in extreme cold. Extreme cold is not a hazard here. Extreme cold is the operating environment. At minus 40 degrees Celsius, air temperature not unusual in the high Arctic in winter, steel becomes brittle, lubricants thicken, electrical systems develop faults that mild weather engineers never encounter. Hydraulic lines exposed to the cold must be kept warm or they lose function. The engineering team on an Arctic icebreaker deployment manages a ship that is operating at the edge of what its materials can tolerate. Every maintenance decision is made with the knowledge that the nearest shipyard is thousands of kilometers away. So the chief engineer on a high Arctic deployment typically has 20 years of experience, a comprehensive understanding of every system on the vessel, and the ability to fabricate replacement parts in the ship's machine shop if the one in stores doesn't fit. There are no other options. The St. Lawrence River freezes. Not all of it, and not all winter, but from Quebec City eastward to the Gulf, and in many sections upstream, the river develops ice from late December through March that would stop commercial navigation entirely without intervention. The St. Lawrence Seaway handles approximately 40 million tons of cargo per year. This cargo does not stop moving in winter. The medium and light icebreakers of the Coast Guard, vessels like the CCGS Martha L. Black, the Sir William Alexander, the de Groseilliers, work the St. Lawrence and Gulf approaches throughout the winter navigation season, keeping the channel open for commercial traffic. The work here is different from Arctic operations. It is not about breaking through consolidated pack ice. It is about managing a dynamic, variable ice environment in a confined shipping channel. Keeping the commercial lane clear, escorting vessels that cannot manage the ice alone, breaking up ice jams before they form into serious obstructions, and maintaining the aids to navigation, the buoys and lights that mark the safe channel, that winter ice can displace or destroy. An ice-displaced buoy in a busy shipping channel is a navigation hazard. The icebreaker crews who reposition these marks are doing it in moving ice, from a vessel that is simultaneously managing its own position against current and wind, with crew members working on deck in conditions that combine cold spray and the physical demands of handling heavy mooring equipment. This is not drama. This is the winter schedule. 11:30 a.m. The CCGS de Groseilliers is escorting a bulk carrier outbound from Quebec City. The bulk carrier, 200 meters laden with grain, does not have an ice-strengthened hull. In the current ice conditions, Category 4 ice in the main channel, she cannot navigate without the icebreaker ahead of her. The escort technique is called channel cutting. The icebreaker proceeds ahead of the escorted vessel, breaking a lane slightly wider than the commercial ship's beam, clearing the broken ice to the sides where possible. The escorted vessel follows in the cleared water, maintaining a safe following distance, typically 1 to 2 cable lengths, that gives her enough water ahead to maneuver if the icebreaker slows unexpectedly. The icebreaker maintains radio contact with the escorted vessel throughout. If the commercial ship encounters ice that the icebreaker missed, a ridge that reformed behind the icebreaker, a submerged ice block that wasn't visible, the icebreaker drops back and works the obstruction. The coordination between the two vessels is the product of established protocols, clear communication, and the experience of the icebreaker officers in managing escort operations. Ice escorting is a service. The icebreaker is not the destination. It is the infrastructure that makes the destination reachable. The helicopter is a system component. The heavy icebreakers in the Arctic carry 1 or 2 helicopters, typically Bell 4, 2 9s, or Sikorsky S-76, depending on the vessel, as operational tools, not passenger transport. The helicopters are used for ice reconnaissance ahead of the ship, for supply runs to communities the ship is resupplying, for search and rescue operations, and for aids to navigation work that requires precision positioning the ship alone cannot achieve. An ice reconnaissance flight from the St-Laurent might cover 200 kilometers of ice ahead of the ship's track, giving the officers on the bridge a picture of ice conditions over the next 12 hours of navigation. The reconnaissance pilot communicates ice type, concentration, and lead positions directly to the bridge. This information changes the course. Before satellite ice imagery became operationally reliable in the 1990s, the helicopter was the only reconnaissance tool available. The ice officer navigated on what the pilot reported, combined with what the officer could see from the bridge. Satellite imagery now provides broader coverage at regular intervals. The helicopter provides current, high-resolution information on the specific section of ice the ship is about to enter. Both inputs are used, neither replaces the other. The hull of an icebreaker requires maintenance that no other vessel class demands. Ice contact wears the hull plating, not dramatically in a single season, cumulatively over years of operations. The bow sections and the ice belt plating develop surface erosion and localized indentation from repeated ice contact. The bow dome, the underwater bow sonar housing, even on vessels equipped with sonar, is particularly vulnerable because it projects below the hull into the zone of highest ice contact force. During shipyard periods, typically every 5 years for a major dry docking, the hull is shot blasted back to bare steel and inspected plate by plate. Any section that is worn below minimum thickness is cut out and replaced. On heavy icebreakers with long Arctic service records, the bow sections may require significant replating after each major deployment cycle. The steel that comes out of a worn icebreaker bow section has been compressed, scratched, and work-hardened by a decade of ice contact. The steel that goes back in is new. The specification for the replacement steel is the same as the original. High-strength, low-temperature rated, weldable with the appropriate filler metals to maintain the joint properties that the original design requires. The welders who do this work are certified for the specific procedures. The inspectors who verify it use ultrasonic testing on every weld, because a poorly executed repair in the ice belt, discovered the next time the ship is in heavy Arctic conditions, is not a shipyard problem anymore. 1455. The St-Laurent has cleared the multi-year ice field and is making way at 8 knots through first-year ice. The passage ahead opens into a lead, a stretch of open water, perhaps 3 kilometers wide, that the satellite imagery showed as clear and that the morning helicopter reconnaissance confirmed. In the lead, the ship accelerates to 12 knots, and the difference is immediately felt in the absence of the hull's working sounds. No grinding. No groaning. The ship moves through the water as any large vessel moves through calm, open water. The crew uses the lead time. Maintenance that's difficult to complete while the ship is in heavy ice, tasks that require steady footing on deck, that require access to exterior fittings, is done now. The deck crew works quickly, knowing the lead has a finite length. The satellite image showed approximately 18 kilometers of open water before the next consolidated ice field. At 12 knots, they have about 90 minutes. The chief engineer has had a pump gasket waiting for favorable conditions. His team has it replaced in 40 minutes. The deck crew retensions a radar mast stay that had been vibrating in the ice. The lead ends at 17:12. The hull begins working again. The crew is back inside. The resupply mission is the work most Canadians don't see. Every summer, the icebreakers that have been working the high Arctic also serve as the primary resupply vessel for communities that have no road access and whose sea access is ice-blocked for most of the year. Resolute Bay, Arctic Bay, Pond Inlet, Grise Fjord, the most northerly, permanently inhabited community in Canada. These communities receive annual cargo, fuel, food, vehicles, construction materials, medical equipment. Everything that arrives by sea comes in the short navigable season, and the icebreaker is the vessel capable of operating reliably in the residual ice that persists even in August. The ship's cargo capacity, the St-Laurent, can carry approximately 2,000 tons of deck cargo and stores, is used to its limit on resupply deployments. Containers of food, fuel bladders, snowmobiles, prefabricated building sections, equipment that the community has been waiting 11 months to receive. The discharge operation at a remote community uses the ship's cranes and the ship's helicopter. A container on a long line, lifted from the ship's deck and flown to shore when there is no dock or the dock cannot accommodate the vessel. The helicopter makes 6, 8, 10 lifts. The ship repositions as each cargo lot is discharged. The process takes a full day, sometimes 2. The community receives what it needs for another year. This is infrastructure in the most literal sense, the physical supply of what cannot be delivered by any other means, by a vessel that has been maintained and operated and crewed with the competence to be in this place, in these conditions reliably. The next generation of Canadian heavy icebreakers is already under construction. The CCGS John G. Diefenbaker, a polar icebreaker designed to replace the aging Louis S. Saint-Laurent, has been in the planning and procurement process for over a decade. The new vessel will be approximately 150 meters long, with 40,000 shaft horsepower and a design capability of breaking through 2.5 meters of level ice at 3 knots continuously. The Saint-Laurent was commissioned in 1969. She has been in service for more than 50 years. Her hull has been replated multiple times. Her propulsion systems have been modernized. Her navigation and communications equipment has been upgraded through several generations of technology. She still works. She still breaks ice in the high Arctic every summer in conditions that no other Canadian civilian vessel could survive. But she is aging, and aging vessels require more maintenance, more downtime, a more careful management of where they operate and what risks they take. The new vessel will not replace the Saint-Laurent's experience. That lives in the people who have served on her. It transfers imperfectly through sea time and mentorship and the institutional memory of the organizations that operate these ships. What the new vessel will do is extend the capability. Deeper Arctic access, longer deployment cycles, systems designed for the Arctic's demands rather than systems adapted to meet them. The Canadian Coast Guard Icebreaker fleet logs approximately 3,000 operating days per year across its vessels, heavy, medium, and light combined. These days represent approximately 40,000 kilometers of channels kept open on the St. Lawrence and Gulf system through the winter navigation season. Hundreds of vessel escorts completed safely, and 12 to 15 high Arctic resupply deployments per year. Search and rescue responses in ice-affected waters that no other vessel could reach. The cargo that moves because the icebreakers kept the channels open, grain, raw materials, manufactured goods, fuel, represents billions of dollars of economic activity that depends on a navigable St. Lawrence through the winter months. The communities that received their annual resupply because an icebreaker was capable of reaching them. These communities do not have a commercial alternative. The icebreaker fleet is not infrastructure in the way that a dam or a port is infrastructure. It is mobile infrastructure. Infrastructure that repositions itself to where the problem is. Infrastructure that anticipates where ice will form and moves before the blockage is complete. Where the ice doesn't stop when the ship passes. The channel of the St-Laurent broke at 3:19 this morning, will begin refreezing by evening if the temperature drops. The ship will be somewhere else by then, and another channel will need breaking. The fleet is always working. The ice is always coming back. Under this video, there's a subscribe button. It's a small action, but it helps keep stories like this afloat. If these systems fascinate you, the quiet force of water held in place by engineering and discipline, subscribing simply means you want to see more of what operates beneath the surface.